When the night sky turned pitch black and Europe vanished beneath endless clouds, bombing became blind guesswork until engineers turned mathematics, magnetrons, and radar waves into technologies and methods that guided Allied bombers with surgical precision. Ground-controlled radio navigation transformed night bombing from luck into geometry. Celestial dead reckoning and other early methods failed under clouds and long ranges, so systems using radio beams and pulse ranging could guide bombers precisely. The German Knickerbein and X-Gerät used continuous electronic beams which provoked the Battle of the Beams and Allied jamming countermeasures. The Royal Air Force's Oboe used two ground stations called Cat and Mouse to range a single bomber and hold it on a circular arc. When the navigator heard a steady tone, it meant the bomber was on course. Oboe was operational in late 1942 and crucial in bombing of Essen. It was remarkably accurate at only 100 radio yard error, but limited to only one aircraft and to a station in England. Later Oboe versions used centimetric wavelengths to reduce jamming vulnerability. The G system allowed dozens of bombers to be guided simultaneously at modestly lower accuracy of around 150 yards, which entered service in late 1943. The US version, called SHORAN, used airborne measurements to two mobile ground transponders, which extended operational reach up to 300 meters under ideal conditions. This enabled a mobile high-precision blind bombing and later geodetic surveying. SHORAN saw limited wartime use, but matured considerably post-war. Each system traded accuracy, capacity, range, and vulnerability to jamming. This shaped bombing tactics, electronic countermeasures, and doctrine for years globally. Ground-scanning airborne radar solved the bomber's central problem of navigating through thick clouds and night blindness. H-2S was a Royal Air Force's first operational ground-mapping radar, which enabled crews to see through darkness or cloud. They could perform blind marking and bombing beyond the reach of ground-based aids. First used on January 30, 1943 over Hamburg, H-2S relied on the cavity magnetron to produce centimetric wavelengths, giving far higher angular resolution than earlier meter-band sets. This allowed identification of coastlines, rivers, and urban complexes. A rotating antenna in a belly ray dome swept 360 degrees, which fed up plan position indicator that produced a map-like circular display. Selectable range scales and later slant-to-ground corrections improved interpretability. Pathfinder Force doctrine adopted H-2S for blind ground marking. Operators were trained to match PPI echoes to pre-prepared radar maps and to select high-contrast targets such as riverbends or industrial clusters. H-2S also reshaped the electronic warfare balance. The capture of H-2S components after a 1943 shootdown revealed the magnetron and spurred German detector development called NACS. This allowed German night fighters to home on H-2S emissions that prompted Royal Air Force to adopt frequency agility, shorter wavelengths, and ECCM adaptations. After the war, H-2S heavily influenced airborne mapping, radar imaging, and electronic warfare doctrine globally. Because only a handful of crews could interpret vague radar images and employ new blind bombing aids accurately, a specialist Pathfinder Force was necessary to create a single reliable aiming point for the hundreds of follow-on bombers. Pathfinders or Number 8 group combined G, Oboe, H-2S, and elite crews to locate targets and lay visual or blind markers so that the main bombing stream could see an attack. Their primary tool was target indicators, a purpose-built pyrocnic flare, candle, spot fire, multi-flash, and parachute sky markers, which were color-coded and used in layered rolls to maintain a persistent aiming point. Early improvised markers were replaced by standardized target indicators, ordnance, and discipline marking doctrine. Oboe-equipped Mosquitoes provided the most accurate blind marking. A single aircraft released precise target indicators through cloud. When ground marking was impossible, sky marking, called Wanganui, placed parachute flares above cloud. Parramatta referred to blind ground marking using H-2S, while New Haven was visual marking by sight. Pathfinders produced pre-prepared radar reference charts and trained intensively in radar interpretation, timed runs, and delivery under all conditions. Another innovation was the master bomber, which was an experienced officer who loitered over the target, used VHF to correct misplaced markers, ordered backers up, and redirected attacks in real time. This centralized control, layered marking, and specialist concentration sharply improved bomber commands and night accuracy and operational coordination. The Norden bombsight was essential to the U.S. Army Air Force's doctrine of high-altitude precision bombing, which coupled an electromechanical analog computer with airframe controls to stabilize the aircraft and compute the bomb impact point. Bombaders input altitude, true airspeed, and wind estimates, while Norden's gyros and tachometric mechanisms track the target image and continuously solve ballistic equations to present a precise range angle and trigger an automatic release. The typical operational use was coupling the Norden bombsight to the Honeywell Sperry C1 autopilot. This allowed the bomber to fly precisely during the final bomb run through the autopilot commands. This reduced pilot-induced errors, holding the plane straight at level attitude during the critical release. This effectively made the bombarder the final controller of the attack. However, practical accuracy depended heavily on crew skill and atmospheric stability. Although the Norden bombsight could model wind drift in real time via the bombarder's tracking inputs, wind shear, jet ream, and turbulence often degraded accuracy. Despite this, the Norden stabilizing gyros, stabilized telescope, and automatic release represented advanced avionics integration. U.S. Army Air Force doctrine compensated for individual aircraft air through formation leader bombing. The lead bombarder used the Norden to aim, and the whole combat box released simultaneously. This method concentrated bomb drops even when precision slightly altered. The Norden was produced widely during the war, and a guarded secret. The combination of Norden bombsight and C1 autopilot was a major technical achievement that requires skilled crews and favorable conditions to approach its theoretical accuracy. High-altitude bombing accuracy depended less on aiming and more on knowing the atmosphere and how bombs behave in it. From 25,000 feet, a bomb falls for more than a minute, and varying wind layers can push it far off course. The solution was to measure the atmosphere precisely, standardized bomb aerodynamics and feed both into real-time ballistic corrections. The biggest single error source was poor wind information. Meteorological units use balloon sensors and radar-tracked balloon flights to map wind speed and direction through the entire column the bomb would traverse. These soundings were analyzed and sent to crews as last-minute meteorological telegrams, so bombers could import recent multi-layer wind profiles into bombsights. Discoveries like the jet ream during the B-29 campaign showed how crucial accurate high-altitude wind charts were. Designers reduce unpredictable in-flight behavior of individual bombs by refining nose-tail geometry, mass distribution, and fusing. When tunnel test and tighter manufacturing tolerances for common bombs lowered ballistic scatter and make trajectories repeatable. Fast photo recon mosquitoes photographed post-rate impacts to produce bomb scatter maps. This helped diagnose bombing errors due to wrong wind inputs and timing issues. Corrections could be fed back into meteorology and bombing procedures. Ordnance teams produced detailed ballistic tables that incorporated drag coefficients and standard atmosphere profiles, so bombarders could quickly convert data into release angles and bomb release timing. Together, these measures turned high-altitude bombing from guesswork into a disciplined, data-driven process. Daylight precision bombing often failed against cloud cover because the optical Norden bombsight couldn't see through overcast. The US initially adapted Royal Air Force's H-2S into ANS-15, and later the higher-resolution AMQ-7, which used centimetric radar to map terrain for blind all-weather bombing. APQ-7's slotted area antenna and narrower beam width allowed operators to match echoes of rivers, coasts, and factories to pre-printed charts. Integration with bombsights combined radar cursor and crosshair into bombing inputs. The radar operator selected a reproducible aim point to the Norden bombsight. The onboard impact predictor computed time to release and then actuated a solenoid would trigger automatic bomb releases. This technology allowed a leading bomber to release bombs through thick clouds, which cued simultaneous releases for the rest of the formation. Centimetric resolution aided target discrimination, with metal roofs, cranes, and rail yards returned strong echoes. APQ-7 was accurate enough to track an industrial facility at long ranges, but not individual structure. APQ-7 increased bombing accuracy against cloud-obscured targets, but it required trained operators and radar reference charts.